Okay, this is discussion 2.1 on classification of matter. So we're going to talk about multiple different ways that you could classify matter in this discussion. So in class, we brainstormed in the chat some different ways that we could think of to classify matter, and people came up with all kinds of things. We could classify them by color, by size, by state of matter, by element, compound, or mixture. We're going to focus on two of those today, which is state of matter and then by element, compound, or mixture. So when we look at the states of matter, one of the things that we talk about to distinguish them is the level of order that they have. So gases are really disordered. Liquids have short range order and solids tend to have long range order. Like imagine something that has like a crystal structure. Okay. Now, when we talk about their shape, we say that shape is definite or indefinite. So indefinite shape means that the substance takes the shape of its container. So gases and liquids both take the shape of their container, right? If I pour my coffee into a different cup, it's going to take the shape of that cup, okay? Solids don't take the shape of their container, though. If I move my pen from room to room, it doesn't take the shape of the room, okay? Volume is a little bit different. So gases have indefinite volume, which means that they fill the volume of their container. Liquids and solids, however, have definite volume. So if I poured that coffee from one cup to another, the shape of it might change to match the cup, but I would still have the same number of milliliters of coffee. Compressibility, gases are highly compressible, right? If you've ever seen like a cylinder of a gas, like an oxygen tank, that's highly compressed oxygen, right? Liquids have very low compressibility and solids are extremely low. So gases are the only ones that have really meaningful compressibility. And then when we talk about their energy, gases have the highest amount of energy. They're moving more quickly. Liquids are, somewhere in the middle, and gases have low energy. One word that you'll hear periodically is entropy. And entropy is just a measure of disorder or randomness in a system. So this increases as molecules move faster and more randomly. So when we think about the different states of matter, which one would have the highest degree of entropy? Well, that would have to be gases, right? They have the most energy, they're moving randomly, they have less of a fixed order and relationship to each other. Now, we can use phase diagrams to predict the state of matter at a substance given a certain pressure and temperature. So this is an example of a phase diagram that shows where this substance would be solid, liquid, and gas. And every substance has its own unique phase diagram. Now, the lines between the states of matter indicate where phase changes are occurring. So I think you probably all know that solid to liquid is melting and liquid to gas is evaporating. Gas to liquid is condensing and liquid to solid is freezing. What you might not have learned before are the transitions between solid and gas. So these do occur, and for some substances, they occur at room temperature and pressure. If you've ever seen dry ice, that's an example of a transition from solid to gas. Okay, it's just frozen carbon dioxide, and at room temperature and pressure, it goes through a process called sublimation. So that's the process of a solid changing to a gas. The reverse process of a gas to a solid is called deposition. And in class, we watched a video that showed the sublimation and deposition of iodine, and that's easily found on YouTube, and I'll post the link on Classroom. Now, at the triple point, all three phases of matter coexist. So imagine ice water boiling. And so often this happens at, a lower pressure and temperature. All right, so pause for a moment and use this phase diagram and see if you can answer the question. So the first is, given a certain temperature and pressure, what's going to be the state of matter? And the second is, what phase change is occurring along line C? So pause and then press play when you're ready to see the answers. Okay, so when we look at this, 200 Kelvin is somewhere between these two lines, the 197 and 216, but it's closer to 197.5, and 5 is just short of this dotted line here, so that's clearly in the solid region. Now line C is between a liquid and a gas, which means that that is evaporation or condensation, depending on the direction that you're going. Now, I want you to imagine for a moment that you're boiling a pot of water on the stove. okay? If you monitor the temperature throughout the process, so once boiling had started, if you monitor the temperature, what do you think you would observe? Just think about that for a moment. Now, many people believe that once the water starts boiling, the temperature will continue to rise. However, once you start boiling, the temperature stays pretty constant. And that's displayed well in this heating curve of water. So what we have here is, imagine if we took a couple cubes of ice and we put them in a beaker on a hot plate and heated it until the ice was water and then until the water boiled into steam, okay? That's what we're basically showing here. So initially, we have ice that's at less than 0 degrees Celsius, so we warm it up. When we get to 0 degrees Celsius, though, we see that all of a sudden the temperature stops increasing. And what's happening there is that the energy we're adding through the hot plate or the stove or whatever is being used to melt the ice. Once all of the ice has melted, it's going to increase in temperature again. So we start with a solid. Next, we have melting in that flat segment. And once all of the solid is melted, then we have a liquid and we are heating up that liquid. When we get to 100 degrees Celsius, the temperature stops changing again. Why? Well, now the energy is being used to boil the water, to change the water from a liquid to a gas, to evaporate or boil it. The temperature will only start going up again once we've boiled all the water, and assuming we had collected the steam, we could continue to heat that steam, okay? So phase changes occur in the flat segments, and in those flat segments, the energy is being used to change the state of matter. Okay? And that occurs when we weaken or break the intermolecular forces between molecules. Okay, so these are the forces that are holding molecules together. And when we weaken them, we melt something. But when we boil a substance, we're completely breaking the forces rather than just weakening them. So that generally takes a lot more energy. When we go from a solid to a liquid, we're really just sort of weakening the intermolecular forces so the molecules can slide past each other. Now, the other way we could talk about to classify matter is in terms of elements, compounds, and mixtures. So this flow chart kind of displays all the different ways that matter can be classified. And initially, we can break matter into pure substances and mixtures. So we're going to talk about first pure substances, and then we're going to talk about two different types of mixtures. So pure substances are basically just when I have one substance with uniform composition, okay? So that would be an element or a compound. So the reason a compound is a pure substance, sometimes that confuses people, but if I have pure water, any molecule I take out of that water will be identical, right? They'll all be molecules of H2O. Now, elements contain just one type of element from the periodic table, and these can't be broken down any further. So any element from the periodic table would be an example: sodium, carbon, nickel, phosphorus. But what about O2? So that's oxygen, like that we breathe. This is still an element. Even though it has more than one atom, it's just one type of element. So that means that it's considered to be an element and not a compound. Compounds, on the other hand, have two or more elements from the periodic table that are chemically bonded together, okay? And since they're chemically bonded, that means they can be broken down, but we would need some kind of chemical means to do that. So you know a lot of examples of compounds: sodium chloride, which is just table salt, carbon monoxide, water. All of those are examples of compounds. And when you look at the formulas, one kind of clue is that you see multiple capital letters, right? Because every element on the periodic table starts with a capital letter. So if I see more than one, it's a pretty good clue that I have a compound. Now we have two different types of mixtures: homogeneous mixtures and heterogeneous mixtures. Mixtures consist of two or more pure substances that are physically joined together, not chemically. So since they're physically joined together, that means they can be separated by physical means. And in topic 2.2, we'll talk more about separation techniques and ways to separate these. In a homogeneous mixture, the solute that's dissolved consists of really, really small particles that are evenly distributed out. So one example would be salt water, right? If I were to make some salt water for some reason and drink it, the first sip of salt water would have the same amount of salt as the last sip of salt water, okay? Air is a homogeneous mixture. When we talk about really high altitudes, obviously there's changes, but just the air in my living room, it's all the particles are evenly distributed. If I walk into the corner of the room, I'm not all of a sudden going to find myself in an area with no oxygen, right? The oxygen is evenly distributed throughout the air. Steel is another example. Heterogeneous mixtures have larger particles, which means they're not going to stay evenly distributed. Often they'll sink to the bottom of the mixture, and so they're not going to be uniform throughout. So for example, mud in water. Muddy water is a heterogeneous mixture because the mud is going to settle down to the bottom. Pulp in orange juice. When you take an orange juice out of the refrigerator, you have to shake it to evenly distribute the larger particles. Now, the last thing I want to talk about here are regions of the periodic table. So we're going to start talking a lot more about the periodic table and sort of delve into it. So metals on the periodic table are to the left side. So there's this bold stair-step line here in the middle. And actually, if you look at the bottom, it tells you which direction the metals are, okay? Everything to the left of that stair-step line. Sometimes that confuses people a little bit, right? They see sodium and calcium and think, well, sodium, salt, how can that be a metal? But remember that sodium and salt is actually gone through a chemical reaction. It's part of a compound. Pure sodium is metallic. Same for calcium. To the right of that stair-step line, we have nonmetals. And along the stair-step line, we have metalloids. In the next topic, when we talk about physical and chemical properties, we'll talk about the different properties of metals, nonmetals, and metalloids. But metals have some properties of both. Okay, so any element that's touching that stair-step line is a metalloid, with the exception of aluminum, which we consider to be a metal. Some important groups you should know. Remember that groups are columns, vertical in the periodic table, and they're important because they share chemical and physical properties. Periods are rows on the periodic table, and they share the same outer energy level. So period 3 has 3 energy levels. Alkaline metals are group 1, and these are very reactive metals. Alkaline earth metals are group 2, and these are less reactive, but still pretty reactive metals. The halogens are group 17, and they're very reactive nonmetals. And the noble gases are group 18, and these are very stable and non-reactive gases. The other groups, you don't have to know special names for them, but these are 4 that you should definitely know. So to practice, go ahead and pause and answer these questions. The alkali metal in period 4, halogen in period 2, alkaline earth metal in period 5, and the noble gas in period 3. Okay, so take a look at the answers. So alkali metals are group 1, so in period 4 that would be potassium. Halogens are group 17, so in period 2 that would be fluorine. Alkaline earth metals are group 2, so in period 5 that would be strontium. And noble gases are group 18, so in period 3 that would be argon. Remember that elements in a group have the same number of valence electrons. Therefore, they're going to have similar physical and chemical properties. In the next topic, we're going to discuss these physical and chemical properties and changes. So let me know if you have any questions, and I will see you next time.